we'll start. B, Roman number 1. Draw the most acceptable Lewis dot dash structure for the molecule SO3F2. Its skeletal is given below. Now skeletal is given. Skeletal is SOOFONF. This is the skeletal. First thing we are doing is, when drawing the most acceptable Lewis structure, when skeletal is given, we are getting the sum of the valencies of atoms of element present in this skeleton, with considering the charge. There is no charge on this molecule, therefore only the valencies of every atoms of elements. Now there are 3 oxygen atoms, 2 fluorine atoms and 1 sulfur. What's the valency of oxygen? 6. 6 into 3, 18. Fluorine 7. 7 into 2, 14. Sulfur 6 into 1, 6. 14 plus 6, 20, 38. From this 38, we have drawn the sigma bonds between each atoms. There are 1, 2, 3, 4, 5 sigma bonds. For one sigma bond, 2 electrons are participated. Therefore, for 5 sigma bonds, number of electrons present in there is equal to 10. Therefore 38 minus 10 to distribute electrons, because from this 38, 8 is consumed for this sigma bonds. Now this 28 are the one which can distribute among the skeletal as either lone pairs or whatever that thing. How this 28 is distributed? Starting from least electronegative one to highest electronegative one, right? Sorry, from highest electronegative one to lowest electronegative one. Highest electronegative one to lowest electronegative one. Now what are the electronegativities of oxygen, fluorine and sulfur? Oxygen is 3.5, sulfur 4.0, fluorine 4.0, sulfur is 2.8. Highest electronegative one is fluorine. Therefore, I am putting fluorine. 28 can be distributed. Now, how much of each fluorine can we put? Maximum of 6. 6, 12. 12 out of 28 is now utilized. We have only 16 left. And next one would be oxygen. Next negative one would be oxygen. For oxygen, the maximum can be put is 6 like this. Now totally 24 is distributed. Only 4 remaining, that can be put this oxygen. And we are marking the formal charges now. Formal charges are, according to the step of drawing most acceptable Lewis structure, -1, -6, 7, -1. There is no -1 fluorine because it's a halogen. this sulfur plus 2. This is the arrangement. Now, is this a stable Lewis structure? Because there is a formal charge distribution. Now, we are looking for whether can be minimized or take it back to 0. Formal charge distribution is 0 will be the most stable one in this one, and there can be no 0 distribution of formal charges, but we are trying to find out is there any structure of particular chemical compound to have 0 formal charge distribution. And can't we form it by displacing one lone pair of this oxygen here? Then this oxygen's electronegativity will be, this minus will be cancelled, and 1 plus from this sulfur also will be cancelled. And doing the same thing for this one too. Then all the formal charge distribution will be 0. Then we can get most acceptable Lewis structure as this one: sulfur, fluorine, oxygen, fluorine, oxygen, fluorine. So we will be displacing these electrons. Now double bond between this oxygen and sulfur, another double bond between 1 2 3 4 5 6 1 2 3 4. Now there is no formal charge distribution within this structure. Now that will be the most acceptable Lewis structure. Since we use dots and dashes, there will be most acceptable Lewis dot dash structure. Next one is Roman number 2. The most acceptable Lewis dot dash structure for the molecule. Another one, H3N3O, is shown below. Draw 2 more Lewis dot dash resonance structures for this molecule. Write unstable and the most unstable structure drawn by you. Now here most stable Lewis dot dash structure is given. What's that? This one, H O N double bond N. This is the most stable Lewis dot structure. Now when this one is given, we are asked to draw the resonance structures of them. How do we form resonance structures from this one? This electron arrangement can be modified in a way to form another structures. How do we modify that? This oxygen, can't we displace this one of this lone pair on oxygen between oxygen and nitrogen and displacing this 5 bond towards this nitrogen? We may obtain another one. Let's write it. O double bond N double bond N. This will be 1. What are the formal charges? Oxygen plus nitrogen 0, this nitrogen minus 1, like this. This will be one thing. Another one, displacing this lone pair here and displacing this one to this nitrogen, we will be obtaining another one. I will write double bond here, H, nitrogen, lone pair, single bond, two lone pairs now, oxygen, two lone pairs hydrogen. What's the formal charge distribution? Oxygen is 0, nitrogen, this nitrogen will be 0 and this nitrogen will be plus. Now we have obtained two resonance structures. They have asked us to write the stability as unstable and unstable and the most unstable Lewis structure. Only unstable one should be named according to them. Out of these two, unstable one would be the one with low formal charge distribution, but formal charge distribution is same here, plus and minus on both. And next thing we are looking for is whether homogeneous charges are present between adjacent atoms. There is no homogeneous charges present between adjacent atom 2. Then the next factor we are looking for is whether a positive formal charge present on an element with higher electronegativity. Here the positive charge is present on nitrogen, here it is on oxygen. Out of these two, the electronegativity is higher in oxygen. Therefore, the one unstable will be positive charge on oxygen rather than nitrogen. Therefore, this will be the unstable one. Then Roman number 3. Based on the Lewis-Dodds structure given below, Lewis-Dodds structure is provided. What is it? FON double bond NC double bond N O CH. 3 lone pairs. Make this lone pairs. Plus and minus. This is the Dodds structure given. What are asked is state the following regarding C, N and No atom given in the above. What are the things as? VSE PR pairs around the atom, electron pair geometry around the atom, shape around the atom, and hybridization of the atom, and atoms are numbered 2. This is a kind of easy one. Oxygen 1, nitrogen 2, carbon 3, nitrogen, this nitrogen 4, this oxygen will be 5th one. These are how it is numbered. But these 4 factors are asked only for oxygen 1, nitrogen 2, carbon 3 and nitrogen 4. What are the factors as? VSEPR pairs, electron pair geometry, shape and hybridization. These are what asked. Let's see around oxygen. VCPR pairs. VCPR pairs means the combination of lone pairs and bond pairs. Around this oxygen one, there are 2 lone pairs and 2 bond pairs. How much of then sum of the lone pairs and bond pairs will be 2 plus 2. Therefore, 4 VSPR pairs present. Around this nitrogen 1, 2 and 3. Now I could mention actually bond pairs means there should be which bonds? Sigma bonds. Sigma bonds. What will be equal to VSPR pairs? Lone pairs plus sigma bonds. These are what's included. How much of lone pairs here? 1, 2, sigma bonds 1, 2, 2 plus 2, 4. On this N2, 1 lone pair, 2 sigma bonds. This is a 5 1. This is a 5 1. This is a sigma, and here will be again a sigma, 2 sigmas and 1 lone pairs. Sum will be 3. C3 1 2. Only 2 sigmas, no lone pairs. N4 1 2 3. Electron pair geometry. Yeah, electron pair geometry regarding VSEPR pairs, we are not considering whether it's a lone pair or sigma bonds. There are 4 VSEPR pairs. Therefore, electron pair geometry will be tetrahedral. When 3 VSPR pairs, trigonal planar. When only 2, it will be linear. 3 again trigonal planar. Shape, when considering shape, we need to consider sigma bonds and lone pairs. What's the shape when 2 lone pairs and 2 sigmas present? Recall the shape of H2O water molecule. Here there is 2 lone pairs and 2 sigmas around oxygen. We know the shape of this one would be angular. This one is called as VO bend shape 2. Right? Around this N2, it's again angular. C3, since there is no lone pairs, electron pair geometry will be equal to shape. Then shape will too be linear. N4, the same thing. It will be trigonal planar here. Hybridization, oxygen 1, 2, 3, 4, sp3, sp2, C3, sp, and N4 will be sp2. So is it done? Problem number 4. Identify the atomic or hybrid orbital involved in the formation of the following sigma bond in the Lewis dot structure given in part 3 above. Numbering of atoms are same. Now, atomic or hybrid orbital should be identified. There are 6. 1, 2, 2, 3, 4, 5 and 6 like this. What are the sigma modes they have considered? Do you see? I'm drawing the structure again. What's this structure? F minus L plus. Sigma modes. What are the sigma modes? Tell me what are the sigma modes first. Now these are the sigma modes. Sigma. One out of these two will be a sigma. One out of these two will be a sigma. This can be either this one or this one. If you choose this one, other one will be the 5 one. And this will be sigma. These are not double bonds. I am showing it as in orange color. Now, how these atoms are numbered? Oxygen 1. Oxygen 1 is this. Nitrogen 2, carbon 3, nitrogen 4 and oxygen 5. These are how it is numbered. Now the first one asks is this fluorine and oxygen 1, this sigma bond. Yeah. What asks is what are the atomic or hybrid orbitals involved in the formation of this sigma bond? Fluorine. What's the atomic or hybridized orbital? This can be said as either atomic or hybridized orbital. If it is atomic, the electron present or given to this sigma bond from fluorine will be 2p. Why? This atomic number of fluorine is 9. Electronic configuration of fluorine is 1:2, 2s2, 2p6. Not 2p 5 can be taken here. 2, 4 and 5. This is how 9 is formed. Now this electron is given by orbital or atomic orbital 2p here. Sometimes in the syllabus we consider it as it is hybridized 2. Both two answers are correct. If we consider the hybridization, or if we are going with hybridization thing rather than atomic orbital, the hybridized orbital would be sp31, 2po sp3. Right? How it is actually hybridized for the since the first example I will tell you. This is the ground state of fluorine. Now you have 2s2 sp3. You have p suborbitals like this, and one s suborbital, right? N2p is 2p1. 1, 2, 3, 4, 5 is present, and 2s 1 and 2 present like this. This is in ground state. After it is excited, this is excited state. How this is arranged will be, you will have 4 sp3 hybridized orbitals. These are the 4 sp3 hybridized orbitals. Right? In this one, in this one, 2, 4, 6 and 7 is yours. The one involved in this sigma bond will be this unpaired electron. That's the reason why we say the orbital involved is sp3 hybridized one. Right? Sometimes it is, but the more correct one I would say sp3, but the 2p answer is also correct. If an oxygen, from this one, from this explanation you could understand oxygens, it's of course a hybridized one. Now atomic orbitals are only given for the peripheral atoms, not central one. Therefore this oxygen will be a hybridized orbital, not an atomic one. Hybridization will be sp3, since there are 4 VSPR pairs. Right? And nitrogen, now this is the first sigma bond. Second one between oxygen 1 and nitrogen 2, or this one. Oxygen 1 we got as sp3, N2 will be, since there are 3 VSPR pairs, it will be sp2. Third one, N2, between N2 and C3, N2 will be sp2, C3, there are 2 VSPR pairs, therefore sp. Fourth one, C3 and L4, C3 sp, L4 will be 1, 2, 3 sp2. Fifth one, N4 and O5. L4 would be sp2, O5 a peripheral atom, therefore it is an atomic orbital of hybridized one. Atomic orbital from the aspect of atomic orbital may be a 2p1. If hybridization taken 1, 2, 3, 4 VSPR pairs 4, then hybridization sp3. Sixth one, L4 sp2 Cl, here will be not 2p atomic orbital, it will be 3p or sp3. Why 3p? It presented that electron involved in the sigma bond present in what? 3p atomic orbital. These are the answers for Roman number 4. Roman number 5. Identify the atomic orbitals involved in the formation of the following 5 bonds in the Lewis dot structure given in part 3 about number in of are same. Tell me what are the 5 bonds first. These are the 5 bonds. You have This is in blue color. You have one 5 bond here, another 5 bond here. These are the only 5 bonds present. And the one asks is, what are the atomic orbitals involved in them? Now you know these orbitals, these electrons participate in forming 5 bond is not present in hybridized orbital like in this sigma bond. We knew that this is N2. N2 was a hybridized orbital with the formation of sigma bond. But here it is 5 bond, it is not hybridized. It present in atomic orbital. What's the atomic orbital involved will be? That's what you need to know. Let me show you how this formation of 5 bond occurs. These are the atoms N2L C3. N2 L, this is the 5 bond, N2 L C3. I am taking this 5 bond here, right here. From the aspect of N2, what's the atomic number of nitrogen? It is 7. Therefore, the electronic configuration of nitrogen will be 1s2, 2s2, 2p3. In ground state, its valence electrons are arranged like this. You have 2 electron is 2s and 3 electrons in 3 unpaired electron in 2p. This is in which state? Ground state. Now in hybrid, when it is hybridized, it's turned into the state called excited state. Now we know the hybridization of N2 is sp2. Therefore, how many hybridized orbitals formed? When it is sp3, you have 4 hybridized orbitals. When it is sp2, 3 hybridized orbitals. When it is only sp, 2 hybridized orbitals. Nitrogen's hybridization here is sp2. Therefore, 3 hybridized orbitals should be formed. These are sp2 hybridized orbitals. In this hybridized orbital, one paired electrons, two pair, there is a one lone pair. This should be present in this hybridized orbital like this. And the electrons involved in this sigma bonds also should be present in hybridized orbitals like these unpaired electrons. Now keep in mind, these are the 2 electrons involved in this hybridized orbital. You know, for this hybridized orbital, 1 electron is donated by this nitrogen. These are the electrons, these 2. Then, where is the other electron present? It means the electron in these 5 bonds given by nitrogen, that remains in one of these 2p atomic orbital. This will be not in hybridized orbital, but will be in atomic orbital. Therefore, this is the electron involved in this 5 bond. Understand that one? Therefore, I explained this thing. Therefore, for the other one, I am directly putting. For N2, you know, it is atomic orbital will be 2p. C3, same thing, 2p. C3, 2p. And L4, again 2p1. Same thing happened in other examples too. Then the last one of part B of the first structured question of 2020. So 2019, right? PI. First one. How are the two double bonds oriented in the elliptic structure given in part 3? What's part 3? Here is the part 3. How are the two double bonds? These are the double bonds oriented in the Lewis dot dash structure given. Two double bonds. Now you know this is the carbon, surrounding it you have two sigma bonds and 2 pi bonds. This is the carbon, and how this carbon, you know, the hybrid. Now this 5 bonds, if this is a carbon, 5 bonds, the electrons present in this 5 bond, it will be in 2p atomic orbital, not a hybridized orbital. Therefore, that electrons involved in this 5 bond or present in this 5 bond remains in this 2p. Right? Now this is what we are considering. And the one here is N2, C3 and N4. If this is the carbon or C3, next thing is let's consider N4. N4 is this one. Surrounding N4 you have another sigma bonds, right? Then another electron in nitrogen, I mean this electron, this one, this electron from nitrogen to from a atomic orbital, since this is 5 bond. That electron also present in a 2p atomic orbital, as I told here. For the L4 it's the same thing, and that one too, an unpaired one, it is formed in 2p. Now our question is how the two double bonds oriented in the Lewis dot structure given below. You know how this is one carbon. The one R's is this one. You have a carbon. What R's is how this how these two 5 bonds are oriented. Right? Therefore, in one carbon, how much of this 2p atomic orbitals are present? There should be 2 atomic orbitals. Why? 2 5 bonds are formed like this. Therefore, there should be 2 unpaired electrons in 2 separate atomic orbitals. This is a one. Another one also would be there. I am drawing a separate color like this. And that electron present like this. And in question, what asks is, how are the 2 double bonds oriented? And this is one double bond, right? This is another double bond. In this one, this now let's get it with regard to the 5 bonds. This is one 5 bond. This is one atomic orbitals gives 1 electron to 1 5 bond like this kind of, like this 5 bond, other one for other 5 bond. Between these two, angle is 90. It means this is perpendicular to each other. Then we can say that between 5 bonds, the angle is 90, or it is perpendicular to each other. This is with regard to 5 bonds. What about with regard to sigma bond? These are arranged like this. What are the orbital involved in sigma bond? It's a hybridized orbital. sp hybridized orbital. The shape of this one is S and P. S is like this, P and like this. Then the shape of this one will be, and the combination of these two, it will be like this. And from here, in this sp hybridized orbitals, 2 unpaired electrons are present either of side, and these are the electrons involved in this 2 sigma bonds, right? These sigma bonds, see, these sigma bonds are linear to each other, while 5 bonds are perpendicular to each other, right? And that will be the answer with regard to sigma bonds and 5 bonds. With regard to double bonds, it will be perpendicular to each other. Problem number 2 of 6th. Give an example of a molecule or ion that has a similar orientation of double bond. What's the double bond here? Carbon, surrounding carbon, there are 2 double bonds like this.
NO2.
NO2 plus can be taken. Right here, L4 and L4 and L2, C3. Surrounding this carbon, you have 2 sigma bonds and 2 5 bonds. NO2 plus can be taken. What is that? NO2 plus, like this. That's correct. carbon dioxide 2 can be taken, and these are similar iron O compound for this orientation of double bonds, right?